Computers are all about computing, and computing works really well in modern computers. So much so that you're trying to compute more and more stuff. By that I mean more and more data that you're trying to transform or condense or do something else. And at some point you're gonna overload the poor computer so much that it will run into an out-of-memory issue. I said issue, didn't I? Oh, corporate speak. I'm not allowed to say the other words. I have to call it issue nowadays. Anyway, running into out-of-memory issues, because all that data you're trying to compute does not fit within your working memory. And that's okay, that's why modern computers have the working memory, your RAM, and a hard drive, or hard disk, or used to. Nowadays we have, well, it's still solid state disks, or whatever else technology-wise you have for long-term storage, which is usually a lot bigger than your working memory. Like if you're talking about high-end PCs, maybe 30, 60 gigabytes of RAM for normal PCs. I mean, servers are a different class. But a couple terabytes maybe of permanent storage. So the data you want to compute is probably gonna sit on your hard drive, not in your working memory, which is an issue because to process it, to run code with it, it needs to be in the working memory. So you need to load it from your hard disk into your working memory and then do your processing on it. And then maybe store the result back on the hard drive. And you have to do that piece by piece because your RAM isn't big enough to hold all your data. Maybe. Or the data could fit on your RAM just perfectly fine, but you don't have it on your machine yet. Maybe you need to download it from somewhere through a network connection. Probably the internet. And for stuff like that, there's a concept, not only in C# but in other languages as well. And the general idea is pretty damn old, because that issue is pretty old, especially in old machines, of course. Memory was very limited, so if you want to process a lot of data, you would have to be creative with how you approach that issue. And the fundamental solution is always taking some of the data and processing it, and then getting rid of that result quickly to make room for a new piece of data. And you pass it on to somewhere else and read some new data, process it, pass it on. And the cool part about the system is that you can have a secondary step of processing that just waits for the first one. So the first processing step in our chain grabs some data from your hard disk maybe, does something with it, and then passes it on to a secondary processing step, which then might pass it on to a third step, which then stores it on a hard drive or sends it away to somewhere. That's something we use, for example, for pipes. For piping, if you have the pipe symbol, this symbol we use for the OR in C#. You might have seen it in command line instructions for your operating system, be it on Windows or probably more likely on Unix systems, where you use it for different programs that all do something very specific by reading some data and then passing it on to step 2 here, another step, and so on. And they all just get one piece of the data and pass it on. And they can do that often, not always, but often on the fly. As in, they don't process all the data at once, they just process the data as it's coming in and then pass it on. And the structure we would use in C# for that is called stream. Or, well, not necessarily the structure we use for that specifically, but the one that encapsulates the idea the best, I think. You might think of this similar to enumerables. Let's go back a few steps. We talk about an array first. We have an array of integers, 1, 2, 3. And this is just a permanent storage, well, sort of, for 3 integer values that I can just access as I want at any time. Just have to give it the index and I can access that specific position in the array anytime I want, repeatedly, without any issues. But our issue we started off with was we cannot store this in one go. That means we don't have access to everything in one go. And that would be similar to having an IEnumerable of int, which might be our array. Right. So with the enumerable, I can't access the individual indices anymore, like I can do with an array, but I still have access to the data. I just have to iterate through it piece by piece. It's like having a cursor. I can only read one value and then move on to the next, which I can read and then move on to the next and read, and then I'm done. And streams are, well, generally they're capable of both of these, but usually would use them in this style. Stream itself is a very basic parent class that has many different child classes, many different classes that derive from stream, which basically just gives us a couple of fundamental methods a stream should provide. Though not every child class gives us a full implementation. I think it's easiest if I just make a stream class myself first, and then we're gonna have a look at how we can use these. Public class, calling it dummy, and we're gonna inherit from stream. And stream has a couple of methods we have to implement. And I'm just gonna let the system do that automatically for me, because I'm lazy. And let's clean this up a bit. That's better. So as mentioned, stream is a very basic class for all kinds of streams, but they can all behave in very different ways. And if you're at some point not sure how your stream will react, what it can do and what it cannot do, you have these properties that give you a quick rundown of what's okay, what the stream is capable of. So the first one, can you read from the stream? Are you able to extract data from it? And usually the answer is yes, but there can be streams where you cannot read for good reasons. Like they're intended to be write only. And you will see later why such a stream might be useful. If you cannot think about a good way for that now, you will see later. Can seek. That refers to the ability to randomly shift between different parts of your stream. The array we had earlier, well, I could just use the index to jump to any point in the array and pick data from there. And seeking is basically that. I'm able to just move the current cursor position inside our large data set to anywhere I want. That's seeking. And many streams are just not capable of seeking because you don't have access to all that data, or you don't have access to it in a way that allows you to just shift where you're reading. Especially if that data is generated on the fly by someone else. In that case, especially in that case, you can't just jump back to a position you've looked at previously or just move ahead to a position way later in your stream. And the last one, can write, is just, can the stream receive information from you? Can you put data into it? This one might be the easiest to understand. Is it a stream I can just write data to? Right, not just to, but is it a stream I can write data into? Can I store data with it? Can I pass data on? Or is it just to get information out of it? Pretty straightforward. Now length, this is where it's getting interesting. length is a property that not every stream will have. Now this is a property, so every stream has this property, but not every stream will give you a proper answer. If it's implemented correctly, then length will give you a proper length if it is implemented in there. And if it's not implemented, it will give you an exception when you try to access it. There's a special type of exception called not supported exception. So throw new support exception. There are a lot of features in the language that use this exception to indicate that something cannot be done. And this is usually for things like stream here, for very general classes that have to cover a lot of different features for very different situations, which are sometimes mutually exclusive. Not always, but sometimes. And the language needed some way to allow this very general class to exist that can do anything in terms of the interface, but where the actual implementations can differ in their behavior. So our dummy stream might not allow us to read. So we set this to false, so I can safely check without getting an exception, can I read? And if I try to read anyway, even if it says false, well, then the stream will throw a not supported exception. And usually you will get also a message telling you what feature you've tried to access that is not supported. So length is the first property we see here, the first thing in stream that might give you an exception if it's not supported. And usually it's in the same group as seeking, because if you have the total length, there's a good chance you have the length because you have access to the entire dataset. Even if it's not very convenient to access it, it's possible. So if seeking is allowed, there's a good chance the length will exist. You can get the length. If seeking is not allowed, probably the total length is also out of reach. That's not necessarily that way. And of course it depends on someone implementing everything correctly, but that's good rule of thumb. Can seek is allowed, is true, then length will also give you value. Position. Well, this is basically what seek is used for. That's the index in our data. So a stream is similar to IEnumerable in that we can always only see one part of the stream. But by changing the position, we can move the cursor, the reading heads, if you will, forwards and backwards. We can set it to very specific position inside the stream, and then we will read from that position. And the same way, you can also read position out to know where we are in the stream at the current state. And then you can remember that and later go back to that position easily if you need to, just for example. Or you can get an idea how far in the stream you are already if you compare it to length. And just like length, this position can only work if the stream has access to all the data at once, or at least a way to access all the data at once. So if canSeek is false, this will probably give you a not supported exception. Going further, let's skip this one for now. Let's talk about read. This is pretty easy. This is your way of accessing the data in the stream. Let's maybe make a simple sketch here. Should see it, there it is. So let's see, I have some pieces of data. Why am I getting wider? Whatever. So this is our full data set. Right, that's the original data. Let's say we have one large data set complete that we have to read through a stream. We have a current position. That might be this thing here. That's position. and that's why we would currently read. And when we call the read method, as you can see, we have 3 arguments. We have an array buffer, and we have 2 integers. Now let's ignore these 2 for now. Let's focus on the buffer. Streams are always about bytes. IEnumerable was, in that sense, not the best comparison because enumerables can be of any type. They're generic. But streams are always focused on bytes. They always revolve around bytes. In theory, you can make your own stream implementations that also offer other types, of course. But fundamentally, under the hood, they always work based on bytes, on pure data. And to include other data types in there, you have to work around that. You always have to make extra infrastructure that in the end works with byte in some way. And when we read, we pass on a byte array that needs to be initialized. This is not an out variable. As you can see, this is just a normal argument byte array. And this array will be filled with data. It's like we are passing on a bucket to the stream to fill it for us. So if I go back to my sketch here, let's say I have an array that has 3 spaces. I'm leaving the top off because this is our array right now. Okay, let's not do that, let's keep it that way. This is our buffer. And this buffer has 3 spaces free. So it has a length of 3 in total. There can be data in here, but that doesn't matter. We just tell the stream, please fill this buffer with the data based on your current position, regardless of if we know the position or not. We pass it to it internally, and then it will take the data from the first, move on the position, second, move on, third, and fill all 3 spots. And this is now the new position after we're done, and the buffer is filled. And because we passed on the buffer, we have the reference to it, so after the read method is finished, we also have access to this data now. Well, actually I made a mistake here. This is not the position. That's my bad. This was the operation in there. This is actually the new position. So we read 3 numbers, so it's advancing 3 steps internally. So this 6 is the next one we would read. This is the new position. We read 3 numbers, we advance the cursor, the reading head, so to speak, by 3 spaces. And there we are now. And the buffer is filled with 3 values from the stream. This is how we read data from a stream. This is the fundamental method for it. There are other ways we can use a read method, but those are built on top of this fundamental idea. We put in a container to put data in. The stream will then fill that container with its data and advance its own position internally. We don't see that. And then we just get to know that it's finished, the container is filled, and we have this integer that will return to us how many spaces are filled. This is important if the stream reaches its end before the container is filled. Look at our sketch right now. The only things left are 6 and 7. I can still give in a buffer, even the same buffer as before, with 3 spaces, an array of length 3. I can still pass it onto the array, to the stream. That's perfectly fine, and it will fill the data until it's finished. Position is advanced to the end of the stream. There's no more data to read, so it will not fill the last spot. This spot will be left at whatever value we initialized it with, or whatever value it had when we passed on the array. And the return value for the read method in this case will be just 2, because we only read 2 values from the stream before it returned. The previous call, where we had 3 values that were filled, we would get a 3. And this is how you can make sure that you know how much data you actually have. You always just compare how much did I get back to how long is this buffer. And so you know, is this buffer completely filled, or is only the beginning filled with data from the stream? Let's talk also about offset and count. This buffer doesn't necessarily need to be a special array just for contacting the stream. It doesn't need to be a buffer in that sense. It can be an array you're actively using for something else, and you just want to fill part of that array with data from stream. It's like you have 2 larger pieces of data that just happen to intersect at one point. So maybe I have another array filled with data. Ah, that's a bad example. We have bytes. Oh, let's use 10. So maybe the first spot is filled with a 10, and I only want these 3 spots filled with data from the stream. I would then call the read method with this array as the buffer, but then I would set offset to 1. Mind 1, 2, 3. The indices, I would tell it start reading into index 1. That's the offset. Offset from the start of the array. If you want the full array, you'd start with an offset of 0. You start at the beginning. Start at index 0. We only wanted to start at offset 1, at index 1. And then we also provided with a count. How many items do we want to read at most? Again, if we want a full buffer, we would pass in a 3. That's the length of our array. But in our case, maybe we only want 2 values. And so it will only fill this one, and leave the last one as it is. So usually, if you just have a buffer that's purely used for reading data en masse, would have the array itself, an offset equal to 0, and the count, which is the length of buffer. Also, count is just the maximum we want to read. So always make sure you check the return value so you know if the stream was too short to completely fill up the buffer, so you don't treat all the data in the buffer as actual data. Now, that is read. And next is seek. Seek is a method that lets you jump to a specific position in the array based on one of 3 points of interest, so to speak. Position was basically the same, but position is always focused on this is an index in an array, to think of it like that. It's always, I'm putting in a value that's the distance from the start of the array. So position 0 would be the very start of the array. Position 1 would be the second byte in my stream, or in the array, or whatever other data structure I have that provides the information to the stream. And position equal 2 would be the third byte, and so on. Seek allows you to set an offset as well, but from different points of interest. So seek origin has 3 values it can be. It can be the origin dot begin. That is the start of the stream, the very first byte. And so offset 0, for example, and seek origin set to begin, that would be the same as setting position to 0. But basically, if you pass in begin as an argument for seek origin, then this offset will be exactly the same as position. On the other hand, you have end, which is the very end of the stream, and so you can go backwards. Offset can be negative as well. Position has to always be positive, because it's always starting at the front, but offset in here in C can be negative, so you can move backwards from the end of the stream. So we have the beginning and the end, and in between we have current, which is our current position within the stream, which might be the start or the end, but it might also be somewhere in between, doesn't matter. So if you don't want to jump to a very specific position and just relative to your current position, you can use seek and just offset by 1 or 2 arrays, by 1 or 2 bytes. Maybe you want to reread some data, you go backwards from your current position and try another read, for example. So seeking is a more in-depth variation of position, moving your head back and forth, your cursor. Set length. This is another very special one. Some streams can be shrunk down or increased in terms of size to fit more or less data. Not all streams have this capability, of course. But if you know what stream you have, you will also know what it's capable of. And when in doubt, you can always just check these variables. If you cannot write the array, for example, and if you cannot seek it, then you probably cannot set its length. So if one of these is false, then you probably can't set the length. And if both are true, that's not a guarantee that you can set the length. So you should always read up what the documentation says about the specific array you have, specific stream you have, or you just give it a try and see if it's throwing a not supported exception. And sometimes even the exact same class can behave differently. That's usually included in the documentation. And setting length can have its uses. The only one I use really is setting length to 0. We're going to talk about that example later. It's rare that I use that. Reading the length, however, that's quite useful in many cases. Setting it, not so much. Write is exactly the opposite of read, which kind of makes sense. That's why it's the same in terms of arguments. We still provide it with an array, with a container with data. Only this time it's not for the array, for the stream to fill it with data for us. This time we provide data to the stream. So it will take the data contained in this buffer and write it at the current position of the stream. And just the same as with read, the offset and count can limit what segment of this entire array you want to write out, in case this isn't just a pure buffer just for the stream and has other uses. You also note how this is just a void method, so it's not returning how many data or how many indices from the buffer it wrote, because either it writes all of the data you provided it, or it will have an exception because it couldn't write it. So with reading, it might reach the end of the array, and so, okay, that's fine. You just return the number of bytes you read. With write, either it can write all the data, or it throws an exception because it failed to do so. And that brings us to flush now. Let's think about the example for I have too much data and can't hold it all in my memory at once. So I offload most of it to the hard disk and only read it piece by piece. When I want to write the data back to the hard drive, I have to actually talk to the operating system. We don't do that directly. Our program, or in general, programs don't have directly access to your computer. You almost always have to negotiate with the operating system to give you access, or to let the operating system handle it completely. So if we want to write stuff to the hard drive from our program, we have to let the operating system know, I want to write something on the hard drive in this sector. This file is the marker for it, this file that you know that you gave the handle to us for. Please write this following data into that sector. And the operating system then will check if you have the proper permissions to do so, if there is any complications, any issues with the hard drive itself, any errors, and it will then start to write the data in there, and will let you know when it's finished and when there are issues while it's writing. And all this extra workload the operating system does costs time, and a lot of that happens once whenever you start telling the operating system to write something. You set out to write some data, you tell the operating system, please prepare data on, or please prepare the hard drive, we want to write data on it. We wait for the operating system to do its thing, and then we start providing it data once it's ready. And that's a lot of overhead actually that can take a surprising amount of time. I mean, maybe milliseconds sometimes, but that is quite a lot in computer time. So writing the actual data can be often very fast compared to the time it took to just start writing the data. If you ever try to copy a lot of files over, you might have noticed that copying a large file, a single large file, is often faster than copying 1,000 different small files that collectively have the same amount of data as the one large file. Because every single file has to basically go through the steps of starting the I/O operation for copying stuff over, writing a lot of stuff that's in the file, and then close it up, everything neatly, make sure it's safely copied, and then pick the next file and start the process all over. It's because you have a lot more overhead. So when we write stuff from our program onto the hard drive, we prefer to write a lot of data in one go over having many smaller attempts of writing a bit of data. Because with every attempt we add overhead. And the less often we have to write through the hard drive, the more time we save overall. So usually you would have some kind of buffer to collect data to store on the hard drive before you actually write it. So even when we call this write method, even if we tell a stream, please write this data, the stream internally might pretend it wrote the data, but it didn't actually do that. Instead, it cached it internally. It has its own buffer internally and holds on to that data you supposedly wrote. It's tricking you. And at some point later, which you don't necessarily have control over, it will decide, I have enough data stored, I will now push all of that out and actually write it to where it's belonging, like the hard drive. And sometimes we want to be very sure that all the data is out and we're secure before we do another step, and that's flush. That is our command to tell the stream, please disregard any internal buffering, any caching, just push the data out and complete the write. Doesn't always do anything. For one, if the write already went out to the hard drive, for example, then flush doesn't do anything anymore because the buffers are empty. And not every type of stream will even use an internal buffer, and so flush sometimes just doesn't do anything. But it's not a bad idea to call it if you're unsure. Also, stream is usually something you want to dispose. And did we actually have it here? No. Okay, so right now Stream is already providing a default implementation for dispose. I can override it. Yep. Override dispose, like that. Yeah, I'm gonna call the base as well. Usually if you have a stream and you dispose it, it will internally call flush first before it closes everything out. So If you forget to use flush, that's not the end of the world, but depending on what you do with the streams, you can run into issues if you don't control this yourself. As far as you can control, at least. I mean, all you can do is tell it to flush now and hope that the implementation actually uses this method. Or you write your completely own version of some stream, which I don't recommend. Okay, so far that's the theory. Let's look at an example of a stream. And since we're talking about storing data on the hard drive, let's use the biggest, most important stream that has to do with I/O. At least in my experience, that's the FileStream. FileStream is the big stream that lets you interact with the hard drive. This is a more or less direct line to the operating system, to its logic about accessing files. And we're gonna create a new file stream, and we're gonna do the full setup, which has, well, first off, a path, a file path to your computer. And I have to actually pick a target now. Where do we put the file? Oh, I don't have a good idea where to put the data. I don't wanna dox myself, so... Didn't think that far ahead. Wait, can I not just... Oh, yeah, that will work. Sure, I don't use it for anything else, so I can use that. Alright, so... I'm gonna use this path. You can see when I pasted this, it automatically added a second backslash in front of the normal backslash. So this is the actual path, but when I pasted it, the IDE automatically escaped it by adding the second backslash. I don't like that too much, so I'm using an @ in front of the string, making this a verbatim string. It basically just tells the computer, this is exactly what I want, please do not do anything with that. Just take it as it is. Ignore that these are escaped, do not escape anything. Take the stream exactly as I wrote it in here. This way I can keep the backslashes and file for writing things. Yeah, just leave it like that. Thing is, I could do something like bin or stuff or txt pdf. I could do any kind of file ending. If you're not aware, file endings are irrelevant. They're just a hint. They're part of the name and they're useful extension to the file name to help you figure out what type of program you should use to read that file, but they don't really affect the content, so you can name this whatever you want. Which is also why you should be careful if you download any kind of file from the internet, because just because it says I'm just a harmless txt or a PDF file, it might actually be an executable that completely wrecks your life. Luckily, not speaking from experience. So, this is our path now. This is where on our hard drive, where in our file system we want the data to be stored, because we're gonna use FileStream now that writes things. That brings us to the next argument. What do we want to do with this file? And I specifically want to create a new file. So I use the option create. Then I have to determine what kind of access do I need. And you might think, I already said I want to create a file, so this should be obvious, but there are differences. Right now I want to write. So I want to target this specific path where I want to create a new file, and the access should be write. I could say read, but that doesn't make sense because I'm needing to put data into the file, not extract it. So file access is basically the direction of information. In which direction does the data flow? I could go for read-write. That would allow me to write data in, but also read it back, maybe to check if the data is correct. But that's a bit of overhead I don't need right now. I just want to write. I can also determine how other systems will interact with this file while I am accessing it. Could, for example, say simply none, which means this file is blocked as long as I am actively working with it. But I could do something like read, which would allow others to read the file but not change it. Can make sense depending on your circumstances. Right now I don't want anyone to access it. Maybe if you're working with bigger important programs where you're afraid that this file might break something by blocking something, you could always do delete, which would allow you to manually interfere with the program by just going into the file system yourself and deleting the file, which might break this part of your code. But causing an exception here might be preferable to having a deadlock, for example. Just saying. But yeah, we're gonna for none right now. And lastly, we also have buffer size. And this is what I mentioned earlier about we don't want to write the data directly, we want to collect that internally. FileStream is one of these. We are caching data internally, and we can determine how much data it should store at most. The default here, at least the documentation says so, is 4000 something. Let's see, it should be 4096. But you can also just leave it out. It will automatically use the default value. If you have very specific requirements, if you know exactly how your program will behave and should behave, you can adjust this buffer. There's not really much merit in doing this, except for very specific edge cases, I think. Like for hyper optimization, if you know there's a bottleneck here and increasing or decreasing this will help me in the long run, go nuts. I leave it as a default usually, and that's good enough. And I don't even look up the default anymore because that might actually be different on different systems. I'm not sure how dynamic that is. Things like the architecture, is it 32 or 64-bit, might have an effect on this. I'm not sure. But yeah, this is a FileStream. FileStream, stream. So that's like that. And because I'm in the new C#, I can leave that out so you can see the entire constructor in one go. Now, file streams are special streams that actually keep system resources locked up. That's why we can do this file share. We can allow other systems to interact with the file because when we open this file stream, we contact the operating system and tell it, this is the file that we want, and these are the conditions which we want for this file. And we get a handle, a file handle from the operating system. Those are like special privilege tokens that allow us to do something in the operating system. Like the OS will check, are we allowed to do this? What are the conditions? Can we do that? Okay, I'm providing you with this special token that lets you do that specific job. If you need to do anything with this file, you can just tell me, this is the token, I'm allowed to do that, and I will do my thing. And these tokens are used for a lot of things, these handles. They're not just for files. There are a lot of different systems on an operating system that use handles fundamentally. Also things like window management, for example. Like this window, this IDE itself, I could request a handle that is used by the operating system to give access for Visual Studio to interact with my screen right now. And I can use another program and try to get access to that handle and do stuff with it. In this case, we're talking about a file handle that will give me exclusive write access to this file in my file system. And as long as I have that handle, as long as that is under my care, no one else is allowed to touch that file, because I specifically requested access without anyone else having any access. As soon as my program closes or my process ends, this handle will be void because it's associated with a specific process. But to make sure that you release the handle as early as possible, so other systems can interact with it, maybe I want to read it with a text editor, or maybe some other part of my program needs to access that file, we're adding this using to make sure that as soon as the file stream isn't needed anymore, as soon as we leave the scope here, we release the entire file stream. And because it's file stream, the dispose will also call the flush internally. Now I want to do a bit more here. So I'm not just limiting it to that scope, I'm actually providing a scope myself using the old school using statements with a block. So it's not releasing when we end the main method, it's releasing once we leave this block here. Now FileStream has a couple of extra methods that we haven't talked about because they're not part of the standard stream setup. There are additional methods that can help us. So we have the write method, sure, but we also have, for example, write byte, which literally just gets a single byte and writes that to the stream, which is sometimes more convenient than creating a byte array to just pass on a single byte. But yeah, that's what we should do. So yeah, buffer equals, actually let's fill it like this, 5 to 9, 11. I'm not sure why I picked those numbers. It's not private. Nice, not a private. No, whatever. Like that, and then we can use buffer. We start with the first position in the buffer and buffer.length, because we want to store all that data. And it's the write method, not the write byte, like that. And with this, we will write this sequence of 4 byte values to the file for writing things on my actual operating system. I'll just call this quickly, see if it's crashing anywhere, but it didn't. And if I check, I do actually have a file in here now called file for writing things with a total size of 4 bytes, which is correct. Now let's try to write a different program. Well, actually, let's just extend this one. We're gonna make a new file stream. We'll just copy the old code here. And this other file stream will target the same file. But this time, we're gonna use open and access read. And file share, we just leave it at none still. Because now we want to read that data out. And we're just gonna create a new buffer. And I'm just gonna make it a bit larger than needed. Well, let's just use 10. Like so. And I'm gonna read. We're gonna get the output of that, and let's make a breakpoint in here. So original code wrote these 5 numbers into the file. This code will then open the file again and read the content into this array here. And I just remembered you cannot see the debug output. That's... Well, if you were able to see it, you would see now the debug output having... Oh wait, locals, that should work. Locals, buffer. should be able to see that. Haha. So buffer has now 5 to 911, that's correct. And the rest is filled with zeros, because we only provided the default buffer and the rest of the bytes were not overwritten. And you can see read bytes only returned 4, because only 4 bytes were read and filled into buffer, even though we provided buffer.length a 10 as count. That's only the maximum. That's how we read data back. And if I just comment out this code and just start the program again, buffer will still contain the same 4 values. It's not reading that from cache, from RAM here, because this code isn't there anymore. This is just a comment. You can also just completely remove it. But it is now reading this from a permanent file on my operating system. That's a FileStream. And now I can show you what I meant earlier with the length method. Actually, let's return, because this is an operation that would write stuff. I can use this FileStream, set length 0. What this does is it basically deletes the content of the file. The file itself will remain. I still have the file on my operating system, but the total size is 0 bytes. It's basically just the registration for a file on my operating system, that's it. And sometimes this can make sense if you just want to quickly delete the content of a file. Maybe you have a text file somewhere that you want to overwrite, or yeah, actually that might be the best example. You have a text file that you want to overwrite, and instead of just writing your new stuff in, you first set the length to 0 to make sure that all the old text is removed. Because let's say you have 10 bytes in the total file and you write only the first 5, you still have 5 bytes of the old data in there, which is not good. You could of course also set it to the total length you actually gonna use later. So I can do this, set length 10. So this total file has now a reserved size of 10 bytes on my hard drive. There's no content. This is basically just zeros now. It's like reserving an array of length 10. Like a byte array with length 10 just on my operating system. Just zeros, no content, but it exists. It is reserved. And so when I now go to the same file and write stuff in there, just go write byte to, let's just write a 2 in there. It's not needing to reserve new sectors on my hard drive. But this is kind of a bad example because I use create. Create actually creates a new file. I should have used open. I think that's what I should have used. Not creating a new file and instead open the existing file and then writing the byte into it. But yeah, the idea would be you reserve the total space you need ahead and then always use that same space. It's like if you think back on to dynamic arrays list, we always started with a certain size of array, and then when the size wasn't enough anymore, we allocated a new array that's bigger, copied all the data over, and then used that new array until that was also too small, and then reserved new array. This overhead of constantly increasing the size of our dynamic array of our list can be reduced by just starting with the full size you need, right? Reduces overhead, you don't run an issue later on while your program is running where, okay, your hard drive doesn't have the length anymore. You take care of all of that ahead of time. So set length can be useful for that. If you know ahead, I'm gonna need this much space on your hard drive, you reserve that ahead, no problem. Or you use set length 0, that's what I use most of the time, at least in terms of set length, to just clear the entire data and start afresh. So that's that part. Now I mentioned that streams always work with bytes, and you don't always want to work with bytes. A text file, for example, I'm just going to rename this now, so we know I'm talking about text file, and my operating system knows I'm talking about a text file, so I can open it with an editor directly. I probably don't want to write individual bytes in here. That's kind of tedious, because I need to know what bytes now. And that's touching upon encoding again. Luckily there is a useful class for that. Actually there are many classes like that, but the one specifically we're talking about is FileWriter. At least for this part. Not FileWriter, sorry, StreamWriter. What am I talking about? StreamWriter gets basically a file stream, in this case, and it can write data into this stream for us. So this StreamWriter has access to this file stream and can put bytes in there for us, and we can provide data to the StreamWriter in form of, for example, this text. Hello. Hello stream. 2 lines. Similar to console output. This will now internally convert these strings into bytes and write those into the file stream and store that in the file. And I think the default is Unicode, I guess. We can also specify encoding, so I could go, for example, UTF-8, which is my default go-to. So now it will encode the data as UTF-8 and store that in the file. Oh, right. That's my mistake. I renamed this to .txt, so this is a different file now, and this new file doesn't exist. I specifically said open, and open means I open an existing file. Please give an exception if it doesn't exist. So I could do it this way, by using the existing file that is still there, or I can go like this and create again. So that will also work. Now I have the txt file as well, and I can open that with a default editor. I'm using Notepad++ right now, and it shows me the text, hello stream. And we can also reverse that whole thing. Let's just copy that over. So we're gonna use the txt one. We open it, we read it, and instead of the StreamWriter, we use the StreamReader. Let's actually remove that part. Still gets the file stream, but the StreamReader will read from the stream we provide. And I can also provide the encoding again. So StreamReader.readLine will give us the full string of the first line. I can do that again for line 2. Thing is, where do we draw the line for the end? Like, what about line 3? Up here, we provided the data, so we exactly know these 2 lines, that's it. Done. Now we are reading. How do we know how much we need to read? How do we know we reached the end? If we read by hand with the read method, we get the number of bytes it read in the read method returned, and we know, okay, this is the end. We read less than the total length of the buffer, or maybe we read nothing. We reached the end of the stream, nothing more to read. StreamReader does things a bit differently. This readLine method returns either the line it read, or it returns null. So if we take a breakpoint in here, Let's call this. And you can see that actually here, first line is hello, second line is stream, and the last line is null. And if I do a couple more lines here, they're all gonna be null. So there's no harm in calling readLine. You're either gonna have a value because there was another line, even if that line is empty, at least you had still the line break characters in your text. But if you have a null, that means there just wasn't anything left. We reached the end of the file. And what you usually do is you create, actually, a loop that just goes through everything and stores it. And here's something we can do. No, thanks. Sometimes the autocomplete isn't the greatest. So we do this StreamReader.readLine not equals 0. Might look a bit weird. What we do is we have first this instruction internally. This is the first that gets executed, and it's the assignment. Keep in mind, this is a single equals. This is an assignment of the return value from readLine into the variable line. Doesn't matter what the value is, we store it in line. But if you remember way back in the beginning, an assignment itself has a return value. And that is the value that was assigned. So this entire bracket now also gets evaluated to whatever was returned from readLine. So we can compare it to null. That means we both stored the data in this variable line and we compared it in this one instruction on top. This is quite common. And now we can do things like console.writeLine, line. We know line is definitely not null, because that's what we checked up here, and it will contain the line if it's not null. We can also do more modern style. And actually, let me just show you that it works first. FileStream, program ended. So there was no infinite loop, it stopped, but it still read everything out. Let's add another line. Line 3. Line 3. Read from the hard drive. And if I open it myself, which you can see, but I can check, it's there. So that code works. We can do a bit more here. String. Actually, let's change this. Do this. Like that. This is also something we can do because this is a newer C# version. Better matching. I'm not sure if we... I think we talked a bit about it, but I left it out. This is a smaller sub-feature. Basically, take the value on the left and check if it is that thing on the right. And that thing on the right means check if it is a string, a non-null string. And we also gave a name here, so it will not just check if it's a string itself, but also will give us a value if it is not null. And store that in this variable line, which exists only in this context. So down here, line doesn't exist anymore, just very local variable. I can think of this entire thing similar to a try block. Like, think of int.try parse, something. We had the out variable. You can think of this in a similar way, just instead of trying to parse something, we just check, is it null? And if it's not null, then give me the value. But if it is null, this will just equate to false. So with a parse it was, if you can parse, then the value will be in here and we return true. And if we cannot parse, this will not have anything useful. The default value would be 0 and we return a false. So you can think of it in a similar way, just a bit fancier. Looks nicer this way. And with these stream readers and writers, we have a bit more flexible access to the data streams, and you can do the same with other data types. So this one is specifically to make text easier, but the other things like XML reader writer, which, I mean, it's still text, but it's specially formatted text. So that's one thing you can do. Oh, wait, should mention that. There's another option we have in these StreamWriters, and actually let's talk about that for the next part. Let's get rid of this stream down here, and then let's keep it for now. So streams exist in a couple of interesting variations. FileStream is specifically for you to access data on the hard drive. Sometimes you want to work with data purely in your code within the working memory, but because the libraries you use themselves expect streams, you need to somehow provide your fully loaded data in a stream. Sorry, something is... Okay, that's done with. That was weird. Yeah, so let's say I have an existing byte array with data, and I want to provide this to some system that expects a stream, like for example the StreamReader we used earlier. There's a special built-in stream we can use for this, and it's called MemoryStream. And MemoryStream can, for example, receive this array from us and store that internally. MemoryStream is just a stream. Well, it is just a stream that we can use to write data to, read data from, etc. And this way we can provide an array to some system that expects a stream. But we can also use it to write data into an array in a way that lets us still interact with other libraries that work with streams. So if I go for MemoryStream write, like write byte for example, just single, which MemoryStream also supports, I can now take MemoryStream to array. That's a special method in MemoryStream which will return the full array of all its content currently. I do this. So let's just step through this. And yeah, it's fine. Create a new MemoryStream. We write a single byte, and then we call toArray. And array is now filled with one value, the 1. Then we do write byte 3, make another toArray, and now we have 1 and 3. And if we look in the debugger here, the non-public members, you can see there is a buffer in here, which is just another array, which has our data. So this is internally a MemoryStream. It's basically like a dynamic array. It's just like list. It has this internal buffer, which will slowly fill up with data. And once this array isn't big enough anymore, if we need more data, it will just create a new array, a bigger one, copy all the data over, and then use that new array to store data. And when we call toArray, it will simply check how long am I, how many positions in my internal buffer are actually filled with real data, and how much of that is just buffer for future data. It will create a new array with exactly that length, 2 right now, copy the data in there and give that back to us. We don't have direct access to that buffer right now. we could have access to that buffer if we provide the array ourselves. So if I go by buffer for 10 elements, that, and then provide that in here, just like I did earlier. Gonna step through this with our buffer. We have MemoryStream, which internally has now our byte array buffer. That's why the length is only 10 and not the 256 it was by default before. Well, let's close this up and just open buffer itself. Buffer is now the array up here that we provided to MemoryStream. I'm writing a byte, and you can see buffer is filled. And the array we get out is still a separate array. Yep. Ah, no, it's not. Sorry, my bad. I mean, it's a separate array, but it's still keeping the same length as our original buffer. But yeah, we wrote the second value, the 3. It's now in buffer, our original value. And we make another 2 array. We get another array, this time with the 3 in there. So 2 arrays still gives you a new array. I did forget that we create the same length as the original buffer if we provide the buffer. Well, then let's quickly check what happens if the buffer is too small. Get this exception. Because we provided the buffer ourselves, the system cannot just replace it, because we hold the reference to it, and this is the buffer it has to use. This is the array it has to use always. We can't have it replace the reference to it, so it throws an exception. Too bad. But yeah, MemoryStream, very useful. It bridges the gap between your internal store data and the streams. Another useful stream. Let's say you have a lot of data you want to store on the hard drive, but your hard drive is limited. When we have so much data that any access to the hard drive would just take forever. So you probably want to compress the data to take up less space, which also makes it faster to access. And one way of compressing it is using GZip, and there's a special stream for that. And now things get a bit weird. So let's use a GZipStream. GZipStream expects a stream from us. It is like a StreamWriter. So we can use, I'm just going to use a MemoryStream now. MemoryStream, just a default MemoryStream. Using around it. New GZipStream will get this MemoryStream. This is the stream it will work with. And we give it now a compression level of smallest size. The best compression the GZipStream offers. And now we can write data to the GZipStream. So let's make it like this. E less than 10,000. Let's make the underscore so you can see it better. And we're just using the existing method write byte because I'm lazy. Convert it to bytes. So it will now write 10,000 values, and because I hard cast it to I, it will just go from 0 to 255 and then start at 0 again. Now this will write the data to the GZipStream. The GZipStream itself will now take that data that I provided, compress it piece by piece, and then feed it into the MemoryStream as we're writing. So as we go on and write more and more data, it will piece by piece take that, compress it down and write it. It's not waiting for all the data to arrive at once and then write it. It will write it in here as we call this method. So if I have a FileStream here, I can generate all that data and have it directly written to the data on my hard drive and don't have to cache all of these 10,000 bytes in my memory. I mean, 10,000 isn't that big of a deal nowadays, but it used to be one. That's 10 kilobyte. That's a lot of memory. Yeah, so that's my memory stream then, and stream.to array. Let's store that. And actually, let's preserve that. Let's make a breakpoint here. So this loop wrote 10,000 bytes. But this array has only 382 bytes because it compressed it. It was very regular data. So it starts at 0, goes up to 255 and then back again. Very cyclical, very obvious pattern, so compression can deal with that pretty easily. Could have been more actually, but this is still pretty good. This is all we can compress on the fly, using a stream that wraps around another stream. Now let's do the reverse. Let's try to read that data. Let's copy this stuff first. We're gonna rewrite it a bit though. First we have a memory stream that's gonna take our array. This is one of those cases where we use the memory stream to wrap around some pure data we have without streams. So bridge the gap. We have to do the exact reverse of what we did here. So we had at the top, so to speak, the input of our pure original data into the zip stream, and the GZipStream then wrote the data into the memory stream. Now we have to do the reverse. We start with a memory stream that has all the data. From that, this stream is then read by the GZipStream, and we are going to read that GZipStream then. And I'm gonna make my life a bit easier here, and just gonna use an array that's already the right size. Byte. Decompressed. New byte, 10,000. Just gonna save myself some time here, for now at least. And then I can go gzipstream.read decompressed 0 length. Just to make sure that everything was read properly, we can do that here. Like that. And I'm setting a breakpoint here. Call the code. Oh yeah, I forgot. Sorry, my bad. I have to change the mode now. We're not doing compression anymore, so I have to reverse the direction. Something you can mix up quite easily. We have a constructor up here that gets a stream and an enum, and here we have a constructor that gets a stream and an enum. They are quite different constructors. This is an entirely different enum. So this compression level, this is purely for compression mode compress, and this is for compression mode decompress. You could also go, what is it? Like that, with default settings, but usually I specify it directly. Smallest size here. And for decompress, well, there is no smallest size, it will just decompress. There's no trade-off to do, so it's just one mode, decompressing. And now we've read it. So we took our original byte array we generated, sort of, 10,000 bytes we wrote, and ended up with an array of 382 bytes, which we then read back out through another GZipStream and the reverse, and decompressed, which is now a full 10,000, which, well, we provided that. We also read 10,000 bytes, and if we look at the content, just 0 to 255 and then starting again at 0. So this is our original array. Decompression successfully. Or decompressed successfully. And of course we can stack this. We can use StreamWriter. StreamWriter equals new StreamWriter. GZipStream. Putting UTF-8. And let's do a couple of things. StreamWriter.WriteLine. Oh, stream. What? Not that. Long text. Like that. Goes in there. Let's simplify it here. And for decompressed, we can do the reverse. We do exactly what we did earlier. StreamReader. We give it the GZipStream coding, UTF-8, just to make sure that's set, and then while StreamReader.readLine is string line. Set line. So we're gonna do this first. Array has this time 59 bytes. This is the content. And this is a lot more than 59 characters, so it did some compression. And this is the output. So that worked as well. And since we're running out of time, let's do maybe one more interesting stream. So usually FileStream and MemoryStream are the ones you will work with most of the time, or potentially just Stream, which you can create directly, but you can store it. So maybe you get a stream from somewhere and you're not sure what it is, so you just use the very basic methods from Stream. But yeah, FileStream, MemoryStream are common. GZipStream is good to know. It's just you have to keep in mind it's a bit weird that you have a stream on top of a stream. They can stack like that. And there's another one that can stack like this, which is very useful, but also potentially dangerous if you're not too careful with it. And that is the CryptoStream. And CryptoStream is specialized for cryptography. So you can encode or decode stuff on the fly. And that's why I said potentially dangerous, because cryptography, you have to be careful if you code it yourself. Look up best practices, and probably best if you don't try to program any cryptography yourself. Just use libraries and check if they are still secure, because these can go bad as well. So if you're using nuggets and external packages, make sure you're always up to date and check for security leaks. And please look up best practices and maybe remarks and good to knows for the systems you use. But there's one special thing CryptoStream does, which is super useful and has nothing to do with cryptography directly, and that is using a base 64 transformation. At least to me it was very useful. So this is what it looked like. We still have, well, let's rename this CryptoStream. This CryptoStream will, just like the GZipStream, get a MemoryStream now, another stream to write data into. So it's just a layer in between. And so I can take this code, I'm just gonna leave the StreamWriter as is. I'm gonna text this text. The StreamWriter will convert that into a byte sequence and feed that into the CryptoStream. The CryptoStream will apply the 2 base 64 transform to convert this byte sequence, but that's all it knows. It knows these are bytes, and will convert these bytes into base 64. If you didn't know, base 64 is just a way to encode data using 64 different characters, ASCII characters, which are very stable, so to speak, because basically every system knows how to understand them, no matter how old, because they're in the ASCII range, so ASCII works, Unicode can understand them, it's fine. And there's basically no system that uses them as special characters, so you can also see them in URLs, for example. So very secure, very stable, very useful for a lot of things. And CryptoStream can make this conversion on the fly. And I had to do that one point where I had hundreds of megabytes of data as base 64. And the program would not let me do that in one go. That was kind of a bottleneck. We actually had memory issues on one system. So this on-the-fly change, very useful. Also, we have this transformation. Usually would have something like this, which is actually encryption. But we're gonna use the base 64 transformation. And we're gonna mode write. We're gonna write something. We're gonna write from some normal data to base 64. Not form. And we can leave the rest of the code like it is right here. And then on this end, we also go for CryptoStream. Let's quickly rename this. And on this end, we also need a transform, but this time it's the from base 64 transform. It also has special argument you can use, but I'm gonna ignore that. And this time it's read, because this time we're not writing to the CryptoStream to encode stuff. We're gonna read from the CryptoStream to decode stuff. I mean, you can also reverse the transformers, but this is what I'm gonna do. And we're gonna read this and then output it like before. Only this time, let's also make something in between. Right, let's... You don't have to convert... No, what was it? No, convert is right. From base 64. Base 64 string, that's it. No! I'm an idiot. I have the encoded data. Okay, sometimes I get things mixed up myself. Get string, that's what I wanted. I'm gonna take array. And a string. It's db, okay, whatever. And if I didn't mess up catastrophically, this should be working. Let's do it in 2 steps. So I did the transformation. Our byte array is now filled with 112 bytes. This is what they look like. And if we convert them, this is the base 64. Can you actually see that window? No, you can't. But this is the base 64 string we got. This is the same text, just converted to first bytes and then to text again, which can actually have users because we don't see any commas or white space or the exclamation mark in here right now. It's escaping, well, no, it's sort of escaping special characters because it doesn't care about any actual characters in here and just converts it into a different string. But yeah, let's continue. I'm gonna feed that back into the CryptoStream and read it out, and this is the result. And if we want to get really crazy, we can... Actually, let's try that. I've never tried that. Yeah, let's just copy this over. So that's the GZipStream. And this is working the GZipStream now, and this is working MemoryStream. And compression, smallest size, like that. Gonna layer another stream in between. This won't work anymore because that's not the pure data we get in there. And then we're gonna do another. Let's just copy this over. This is just for my own curiosity. Just want to see this now. Stream, that's compression mode. Decompress. And this is using the GZipStream. This should still work. In theory, you should get to see that on the output. Let's make a breakpoint to see how big the text is. Okay, so that worked. You can see the output. And if we check array, 93 bytes. So the original data converted to base 64 and compressed, and then returned through 3 layers of stream. All right, that's the last one I wanted to show you still. Instead of doing it with the StreamWriter, what we could also do is use another MemoryStream. So I'm just going to show you the alternative, because that has other applications as well. And using MemoryStream, let's call it output. Yeah, it's fine. New MemoryStream, default buffer. And then we can use CryptoStream.copy2. And this will get another MemoryStream. Copy2 is just a method to just tell the system, hey, you have stream A, copy everything you can get from stream A to the stream B I'm passing on as an argument. Copy CryptoStream into output, everything you have. So when we do this, we'll copy everything into the output MemoryStream. If we check in here, this will now have 97 bytes. And these would be what we read with the read line here in the StreamReader. But because we're using a stream, we actually have an interesting scenario here where the StreamReader doesn't see anything anymore. We've copied everything to output in here. Everything. We reached the end of the stream. And so when the StreamReader is tasked to read again from CryptoStream, well, there's nothing more to read. We already reached the end. We've read everything because we only read once. And so what you want to do in this case is either set the position or do a seek. Do it a bit more formal. And I'm going to see it to set length and then again. Right? So that's what you would do to reset everything. But that doesn't always work. Thing is, fundamentally, we could do that. We can reset everything, go back, because the original source for the data is this memory stream with an array. And this memory stream, we can reset that, no problem. But CryptoStream itself doesn't support seeking, if you can see in this error message. So even though the source data can be sought, what's the past tense of seek? Seeking? Sought? Yeah, right, sought. Sought after? Doesn't mean that the streams we stack on top will. So to do both of these, we're gonna have to move this down here. Instead of CryptoStream, we're gonna do that with MemoryStream. And we're gonna copy all of this over and do it a second time. Or not. Because we can also just try to do it this way. Honestly, I'm not sure if this will work. No, didn't work. Yeah, we have to do that from here. So after that's done, copy this over. And the first one is going to use the memory stream to do that. No real use in that. And the second one is going to do this. And I forgot this one. Oh no, wrong line, that's it. Okay, so good, I forgot that one as well. Right, this is the argument I forgot to mention, or not forgot, but left out for the StreamReader. This GZipStream, for example, has an additional argument I can put in, a boolean called leave open. And this CryptoStream here also has that. And actually a StreamReader itself would also have that. So StreamReader, yeah, it's a bit special. There are some other arguments, but leave open exists here as well. And the thing is, let's actually, no, that's enough. This should work now, just to demonstrate that it's fixed. I passed my memory stream into the GZipStream, so it has now access to this memory stream. And my CryptoStream has access to the GZipStream. The default behavior they have is, I pass the stream to you that is now tied to you. So you belong together now. So the default logic would go, I don't need this CryptoStream anymore, I dispose it. I'm done. Then also dispose the underlying stream because it is tied to you. If you not need it anymore, then they're not needed anymore. And so the chain goes down to MemoryStream. So once we dispose CryptoStream in this line, once we leave this, it will also dispose the GZipStream and the MemoryStream. Technically, I would not need to make any usings here. It's just not necessary in that case. But if I do want the MemoryStream, for example, to persist after these two are done, if they are not tied together, because I, for example, reset the MemoryStream and start again, then I need to provide the argument true to make sure that these do not dispose the underlying stream as well as themselves. I have to specifically tell it, leave it open. Do not touch it. Even if you dispose, do not dispose it. That's why I have to use using for every single one. In theory, you can leave that out, and even if they are disposed, dispose itself is intended to be safe to call even if it was disposed. So even if an object is disposed, you can always call dispose again. So once we dispose CryptoStream, the GZipStream is already disposed. So if we leave the using block here and we call dispose internally, it will just dispose it a second time, that's safe. And the GZipStream will, when disposed, call the MemoryStream dispose, which is also safe to do even though it's disposed. But because of that, the GZipStream did dispose the MemoryStream. And so once we reach this line, even though we're still in the using block of the MemoryStream, it was disposed. Alright, for MemoryStream, instead of seek, I would always go position, usually. Same result, it's exactly the same behavior. This would be the less formal one. I have a specific position, just set it to the beginning. Done. And with that, we're finally done. That is streams. They're used a lot, and sometimes there are combinations of them because the idea is either you have a stream because you can't hold all the data at once, or because you cannot get all the data at once, because it's network operation maybe. And sometimes the idea is I want to have some kind of mechanism to transform data through several steps on the fly. Because I can afford the offloading the data into the memory. Maybe that's possible, but I just don't want to waste those resources because why bother? If all I'm doing is maybe read a file from the internet, then do a couple of steps to read the input and just write some stuff to the console output, why should I download everything and then do the operation. I can do that on the fly. I don't have to hold all the memory, saves memory space, and I don't have to wait for the download to complete, so I'm faster, so cool. That's what streams are for. And your homework. Your homework will be to twofold. One, try to implement your own MemoryStream. Just fulfill the basic criteria to be a stream, and then implement it in a way that lets me store data in it as if it was a list, dynamic array. So mimic the behavior of MemoryStream, including a method to array that will give me the entire content. Create your own stream that internally behaves just like a dynamic array to accept data to store it in there and to read from there. That's your homework. Alright, that's it. Bye bye.